Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list, published on August 21, 2025, just yesterday. The standout claim is that it materially narrows the open and closed source gap in scientific multimodal reasoning, even surpassing closed source state-of-the-art on professional tasks like molecular synthesis planning and reaction condition prediction. The paper is titled Intern-S1, a scientific multimodal foundation model. And as we will see later, the implications for large-scale training and reinforcement learning are quite significant. In short, it introduces a multimodal mixture-of-experts model trained on 5 trillion tokens with a mixture-of-rewards framework that scales online reinforcement learning across more than 1,000 tasks. Also, the author shared a GitHub repo. You'll find a detailed README with model overview and benchmarks, links to Intern-S1 and Intern-S1 mini-weights, quick start code for text, image, and video via transformers, recommended sampling settings, serving guides with VLM, LM deploy, SGLang, and Olama, tool calling examples, thinking mode controls, and hardware requirements. Alright, let's unpack this chart. The scatter plot shows performance on general tasks along the horizontal axis, and performance on science tasks on the vertical axis, so you can see how progress differs across domains. The blue path trends upward in science as general ability rises, while the red path improves mainly on general tasks but slides down on science. The takeaway is a widening imbalance. Gains in popular benchmarks do not automatically translate into scientific capability. Building on that, this figure plots 2 scatter panels, comparing general performance on the horizontal axis with science performance on the vertical axis. The left panel covers image and text benchmarks, where the yellow star sits above and slightly left of several blue points, indicating stronger science ability at similar general scores. The right panel shows text-only benchmarks, and the yellow star again leads, positioned high and near the upper mid-range of general ability. The consistent placement signals balanced gains that lift science results without sacrificing general skills. Next, we have the system diagram that ties everything together. The central flow shows a mixture-of-experts large language model on top, which receives 3 projected streams: images via the vision path, scientific strings via the dynamic tokenizer, and time series via a specialized encoder. On the left, the Intern-VIT encoder feeds pixel unshuffle and an MLP projector, so visual tokens align with language space. In the middle, the dynamic tokenizer switches tokenization and embeddings for scientific data versus natural text. On the right, adaptive downsampling prepares long signals for the time series encoder before projection. Now, this table summarizes the decoding setup used for evaluation, which matters because sampling choices can shift scores noticeably. You can see both models use 65,536 max tokens and top P at 0.95, with top K at 50, and a repetition penalty of 1.0. The only deliberate difference is temperature 0.7 for the larger model and 0.8 for the mini, so the smaller model samples a bit more freely. Wrapping up, the big picture is clear. Scaling a mixture of experts with science-specific data and encoders unlocks balanced gains, and the mixture of rewards pipeline makes large-scale online reinforcement learning practical across 1,000-plus tasks. Together, these choices narrow the science gap without sacrificing general skills. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.